I'm actually going to go ahead and start recording this in case Michelle is unable to make it, then at least I can post this online and she can get caught up on the notes. So just for Michelle's sake, I'm going to quickly go back. I didn't think about it till just now. I'm going to quickly go back and just show the slides so she can at least see them on those first two. And then we'll move on. So Michelle, if you're watching the video, we're doing 211 and it's about truth tables and logic expressions. This is what we're going to be covering. So I'll let you read that. You can pause the video and read through that. We've just been talking about these key points of how we design truth tables. And so you can pause the video and get these written into your notes. And then for all the rest of you, you hopefully have that done by now, and we'll just keep moving forward. All right, so constructing a truth table. If you look at this truth table, you'll see on the left we have inputs of X, Y, or Z. And then there's going to be, for now, just one output column, and we're just going to call that F. I think they take the letter F just to kind of think of almost like a function notation. And so that's where we're going with that. But you can really use whatever. You could use O for output. Doesn't really matter. It's just variables. But if you look in the X, Y, and Z columns, you can see that they're counting down. There's 3 inputs, which means we have 2 to the 3rd power of combinations. So there has to be 8 combinations, which means we'll count from 0 to 7 in binary. So the first row is 0. The second row is 1 in binary. The next row is 2 in binary, and then 3, and then 4, and then 5, and then 6, and then 7. So these always have to be in order based on binary count. So hopefully you're really comfortable with binary count now that we've been using it for quite a few lessons at the end of Unit 1. If not, you may need to review back a little bit, but a quick summary of how it works. This first Z column, that is worth 1. So anytime there's a 1 in that column, it's a 1. The Y column is worth 2. And then the X column is worth 4. It's that if you're converting back and forth from binary to decimal, we use 2 to the 0 power, 2 to the 1st power, 2 to the 2nd power. So this is 0 because they're all 0. 0 plus 0 plus 0 is 0. This is 1 because anything in this Z column is worth 1. And that's the only thing that's there. This is 2 because anything in the Y column is worth 2. The next one's 3 because it's got a 1 in the 2 column and a 1 in the 1 column. 2 plus 1 is 3. And then this is a 1 in the 4 column and 2 zeros, so that's a 4. A 4 plus 1 gives me 5. A 4 plus 2 gives me 6. A 4 plus 2 plus 1 gives me 7. So if you remember the first column Z, first column on the right, Z, is always worth 1. This next is 2. The next is 4. The next would be worth 8. You just add up any ones and it gives you the total number. And so we always need to put them in binary order. And then the output is telling us, okay, if X, Y, and Z are all off, the output should also be off. But if Z is on, the output should be on. If Y is the only one that's on, the output should not show up. It should be off. But if Y and Z are both on, then we should get an output that's on. If the X is on, the output should be on. So that's what the truth table is helping us to predict. And you may notice that when Z is on, there's multiple times when you get an output that's 1, but then there are 2 times when you get an output that's off. So we have to consider all the combinations. There's maybe multiple sensors and we're looking for specific combinations to give us an output that's on. So there's only 1, 2, 3, 4 combinations of inputs that actually tell the circuit or tell the output of the circuit, you need to turn on the siren or you need to turn on the light or whatever happens to be the buzzer. There's only 4 combinations that would create that positive output. All right, so if you're making the truth tables with 2 inputs, 2 squared is 4, you're going to have 4 combinations. So you count from 0 to 3 in binary. If you have 3 inputs, that's 8 combinations, 2 to the 3rd power. So you go from 0 to 7 in binary. If you have 4 outputs, that's 2 to the 4th power or 16. So you count from 0 to 15 in binary. So your input columns will always be identical, counting in binary. Your output's really the only thing that you're going to be adjusting. So once you get comfortable with creating those truth tables, you should be able to just put the inputs, figure out how many you need, make your table just filling in by counting in binary, and then depending on what the circuit shows you or what the demands of the design show you, you decide in your output, well, would this combination give me an on or an off signal? So just a quick review of how, depending on how many inputs you have, you'll create a different sized table. But the inputs will always be the same, starting at 0 and counting up in binary until you have enough combinations to satisfy the number of inputs. All right, so now how do we go from a truth table to a logic expression? So I'm just going to put these steps up here, and then we'll talk about the example in a second. I'll give you a few seconds to write down the part in red, and then we'll talk through this example. All right, so we've got our truth table here, and the steps tell us if we're given a truth table, the way we write our expression is to consider what's called min terms. And min terms is an abbreviation for the terms that minimally satisfy our expected result. So depending on the design we're trying to create, there are the terms of our inputs that minimally satisfy what we're trying to create. So it says write the min term adjacent to each row in the truth table that contains a 1 in the output. So if we look down at this table, you can see there's a 1 in the second row, there's a 1 in the fourth row and the fifth row, and there's a 1 in the seventh row. So beside each of these rows, we're going to write what we call a min term. So let's show that part first. The way we write min terms is you look at the input letters. So we've got our inputs of X, Y, and Z. If it's off, you put a line over it. That means it's not on. So what you'll often hear me say, and you'll hear it phrased as we've got this first min term in row 2 would be not X, not Y, Z. In other words, the X is not on, the Y is not on, but Z is. So that's how we write that min term. In the fourth row, we would write not X, Y, Z, because the X is not on, but the Y and the Z are. In the fifth row, it's X, not Y, not Z, because the X is on, but the Y and the Z are not. And in the seventh row, we write X, Y, not Z, because the X and the Y are both on, but the Z is not. So we just write down the code, basically, of the 3 inputs that give us the correct result. All right, the way that we do the sum of products logic expression is by just adding those together. So we've got not x, not y, z, plus not x, y, z, plus x, not y, not z, plus x, y, not z. So that is what we mean by a logic expression or sum of products. So you can see the second dot up here at the top, write the sum of products. It literally is, they call it that because these four terms, these four min terms are like your products, what you're expecting to give you the correct positive outcome. And we call it a sum of products expression because we're putting plus signs between each of the min terms. So hopefully you've had a chance to write down those two key red descriptions and the example so you can understand how to convert from a table to the min terms, and then writing down the expression, which that's the easy part, is just rewriting the min terms in a logical expression, putting each min term in a mathematical expression, so to speak, with plus signs separating them. Now, sometimes for a very complicated example, for a very complicated truth table, it might be helpful for you to actually write these min terms down beside the table. Other times, like this one, I would say you could probably just go directly from the table to the expression and not necessarily need to write down the min terms beside the table. But you're going to see that as we move forward, you can have multiple cases where you're going to be canceling things out, combining things, and so writing them down beside the table can be extremely helpful.
So do we need to simplify it any further, or is that just like the final answer?
No, that's going to be the final answer. We'll talk about simplifying it a little bit later, and then in future lessons, we're going to learn some specific strategies for simplifying it. But for now, this is all you need. Is there anybody that needs more time on this slide to get everything down? Not seeing any hands or hearing anybody. So I assume that means we're good to go. All right, so what I'd like you to do, write out a SOP logic expression for this output, for this truth table. So whether you want to copy down the truth table or you just want to look at the screen, I want you to write out the SOP expression and put it in the chat so I can see if you're on the right track.
How do you write not in the chat? Should I just write not in front of it, or like?
I usually put like an apostrophe beside it.
Oh, okay, perfect.
Yeah, good question. I didn't think about that. So for instance, I'll type the first one just so you can see how it would, it usually is written not A, not B, not C, D. So that's how you could write it. And actually, I think that's the format you use. There's going to be something I'll be showing you in January at some point inside of Multisim where you can use this kind of notation. So that would be the first min term in row 2. So go ahead and that's the first min term in row 2, but go ahead and add all the other min terms. So anywhere there's a 1 in the F6 column, you'll put them together as a sum. So yeah, like Nico, I haven't checked it, but Nico's got the right idea here where you're putting them together in a pattern. Yeah, and Andy's got the right idea. All right. Looks like most of you are getting this figured out. So let me go ahead and start revealing the answer here. You should have 5 min terms in your expression. The first one I already talked to you about, not A, not B, not C with D. And the second one, not A, not B with C and D. The third one, A with not B, C, and D. The fourth one, A, B, not C, D. And the last one, all on, A, B, C, D. Okay, so hopefully that's making sense. That's how you write the expressions. The first part of your assignment today asks you to look at truth tables and convert them into expressions like this. That's the kind of first step. All right. So for each term in a logic expression, we're going to place, now we're going to go the other direction. We're going to figure out how we can take a logic expression and make it a truth table. So for each term in the logic expression, we're going to place a 1 in the output column that matches. Some terms might match more than 1. So we'll look at this example. If this was the logic expression, it's going to give us an output of 1 when X, Y, and Z are all turned off, when they're all not. It's going to give us an output of 1 whenever both X and Z are on. And it's going to give us an output of 1 when both Y and Z are on and X is not. Okay, so those are the 3 situations that give us a positive output. So when we set up our truth table, the X, Y, and Z columns are always going to be the same. Start at 0, 0, 0, then 0, 0, 1, 0, 1, 0. Just going to count in binary straight down and fill those in. So the input side's easy. The output side is, okay, we need to figure out where are they all not? And so that's going to be the first row. And then where are both X and Z on? And X and Z are both on in the last row and then 2 above that. And then where is X not on but Y and Z is? And that is in the 4th row. So we can see those are the options where these min terms are satisfied. And so we put 1s in those boxes and we put 0s in all the others. So this is just helping you connect, oh, how could I do this backwards? What if I wasn't given the truth table, I was given the expression, how could I create the truth table? And you're also going to be doing that in the lesson. So it starts off asking you, okay, here's a truth table, write your expression. Then it says, okay, here's an expression, write the truth table. So earlier, Andy, you asked about simplifying, right? So this is kind of showing a simplified one. These bottom 2 that are like row, the 6th and the 8th rows here, they both are a case where the X and the Z are both on, and it doesn't really matter what the Y is. Whether the Y is on or not, it still gives us a positive output. So rather than having 2 separate min terms, X, Y, Z, and X not Y, Z, they just put X, Z because Y doesn't really matter. No matter what Y is, it's still going to give us a positive outcome. So there they've just shown that you can kind of simplify it because as long as X and Z are both on, it doesn't matter what Y is. Both values for Y still give us an output of 1. So that's one way you can simplify. Now, as you're doing your assignment, you don't necessarily have to simplify. Okay, so if you don't notice something that can be simplified, you're not going to be counted wrong. But if you can simplify it, that's great. And if not, that's not a problem. It's often they will give you simplified expressions that you have to convert into a truth table. We're going to learn some specific techniques for simplifying later. So you don't really need to worry about whether you can simplify yourself or not yet, because we're going to learn those techniques later. Any questions about how to do this backwards, going from an expression to a truth table? All right. So if we think about this example, they're kind of showing you the truth table for A, not B, C, D, not A, not B, A, not B, not C, not D, B, not C, D. And so you can see there's a lot of outputs that are on for this example. I would always start with the ones that have all four inputs listed. So A, not B, C, D. That's going to be close to the bottom because you got most things on. So it's going to be the third from the bottom. No, sorry. The 1, 2, 3, 4, 5, sixth one from the bottom. A is on, B is not, C and D are. And so the ones that have all four terms are usually the easiest ones to go back into the table and fill in. And so I would do that A, not B, C, D first, find that, put a 1 there. and then A, not B, not C, not D, the other one that's got all 4 terms, that's a pretty easy one to find too. That's like about halfway down the table where A is on and everything else is off, and then you put a 1 there like they have. Then you go through and say, okay, well, when are all the cases where both A and B are off? And that would be the first 4 rows. A and B are only both off in the first 4 rows, so all those get a 1 in the output. And then how about when B and D are on, but C is off? So we want to try to scroll down and look, okay, when are all the times when B and D are both on, but C is not? So I don't know if you can see my cursor very well, but right here, what is that row? Let's see. It's binary count 6. That one has B on and D on, but C off. And then we scroll down again. Where else do we see that combination? Down here in binary count, let's see, 8, 12, 13. Where we have B on, D on, and C off, so it fits that one as well. All right, so that's how you can go from the expression. I would start with the ones that have all 4 terms, put the ones in the columns where they go, and then try to get the ones that have been simplified after. Questions about that example? I'll let you kind of absorb it for a few seconds. So if the min term in your expression has 4 variables, then that means there's only one thing. There's only one row that will be satisfied by that. But if it has fewer, then it's going to satisfy multiple rows. So the one that only has 3 variables satisfies 2 rows. The one that only has 2 variables satisfies 4 rows. All right, just about done. Just want to talk about how we can also go from a design, and this is what you'll be finishing up with in today's assignment. Going from a design and then creating a truth table, coming up with the expression from that. So the first thing when you're trying to design something is figure out, okay, well, what is the number of inputs that I need? And then you're going to assign variable names to those conditions and figure out, okay, well, which of these would give a 1 for an output and which would give a 0 for an output? And then you're going to create the truth table. It's kind of the steps of what you would do to go through a scenario that has a design actually for you. So here's the one we're going to look at. We have a large fuel tank that has sensors that monitor temperature and pressure. Both sensors output a logic low if they are within safety range. So basically, if it's safe, it gives a low signal. An alarm will sound if either sensor indicates an unsafe condition is present. So if either one of those turns on, then the alarm's going to go off. So the alarm is the output, and the inputs are temperature and pressure. So we're going to create a truth table for this, and then we'll write the SOP for it. So how many inputs are there? You can just unmute and say it.
Would it be 2?
Yeah, 2, temperature and pressure. And so we'll probably use like T and P, makes sense. And then the output, there's just 1, alarm. And so we could just use A, choosing variables that make sense in our truth table. How many rows does our truth table need to have if there are 2 inputs?
4.
4 rows. So what are we counting from and to in binary? Where do we start and where do we finish in our binary? Count from what to what?
0 to 3.
0 to 3. All right. So here is our kind of summary of what we're doing. We've got a pressure sensor. It's safe when it's off, unsafe when it's on. We've got a temperature sensor, safe when it's off, unsafe when it's on. And then we've got an alarm that's we're going to use a signal 1 when we're saying the alarm would go off in that condition, and we'll show a signal 0 when the alarm would stay off. The alarm would turn on, I guess would be a better way to say it. All right, so if we make our truth table, it's going to have 0, 1, 2, and 3. Just looking at the P and T, that's just our binary count, right? 0, 1, 2, 3 in binary. And then for our alarm, if both the pressure and temperature sensors are off, the alarm's off. If the temperature sensor turns on, the alarm turns on. If the pressure sensor turns on, the alarm turns on. If they both turn on, the alarm turns on. Okay, so this would be going from a design where you have a problem to solve. You have to figure out, well, how many sensors do I need? Okay, that tells me how many rows I need in my truth table, and probably want to give them logical variables that make sense. And then for my output, what conditions should give me a 1 output? And the inputs always just count in binary, and the outputs, you just put a 0 if it doesn't satisfy the conditions, and a 1 if it does. So that'll be kind of what you'll be ending up with in the lesson, is looking at a condition or a set of conditions and creating a truth table from a word problem like this. All right, so let's see if we can talk through this last one here. Your teacher keeps final exams in the office. For security reasons, you're asked to design an alarm system for the office. The office has a window and a door that are equipped with sensors that output a 1 when they are secured, when they're closed. When the alarm system is turned on with a key, a siren should sound if either the window or the door is unsecured. So the alarm is the output. How many inputs?
3.
3. What are those inputs, Carter?
It'd be the window, door, and the key.
Good. All right, so if we have 3 inputs, how many rows does our truth table need?
4.
We're going to do 2 to the 3rd power. If there's 3 inputs, we do 2 to the 3rd power.
8.
8. So what are we going to count to and from in binary to get 8 rows? From what to what? Now, someone may have answered because you all froze for a minute. So what are we going to count to and from in the table to get 8 rows? Can you guys hear me?
7.
7. Okay, good. 0 to 7. We got a little choppy there, so I wasn't sure how much you were hearing. All right, so here's our situation. We've got the key as an input. We've got the door as an input. We've got the window as an input. And then we've got the siren or the alarm as our output. All right, we're going to count from 0 to 7. So go 0, 1, 2, 3, 4, 5, 6, 7. We've got key, door, window. They've used S for siren instead of A for alarm. Doesn't really matter. It's just a variable. And then we need to think through, okay, if the key is not in, the alarm is not turned on. So for all the ones when the key is off, we don't have any output because the alarm isn't even activated. So now we really just need to focus in on these bottom 4 rows. When the key is turned on, if the window and the door are zeros, because here it shows it's a 0 when they're open, right? So if they're both open, the alarm goes off. If the window's open, the alarm goes off. If the door is open, the alarm goes off. And then if they're both closed, because remember ones mean closed, if they're both closed, the alarm stays silent. Okay, so in this case, they've kind of reversed it where they're saying it's when it's open that you get a positive output. Okay, so it's when there's zeros that you get a positive output in this case. And just showing you this one so you can see you can actually use on signals to give an output that's positive, or you can use off signals. Now, just a little bit of curious here. What kind of logic gate could we use if we want to have an off signal give an on output? What kind of logic gate? We've learned 3 logic gates. Well, we learned more, but primarily 3 we focused on. Which one would take an off and make it on?
An inverter.
An inverter. All right, so that's going to be coming in lessons next week. Or I don't even know if we'll get to that next week. It might be actually a little bit more after Christmas break, but we'll be moving from this logical part, kind of conceptual part, to actually building the circuits. Oh, I would need to use an inverter there. I would need to use an AND gate there. I'd need to use an OR gate there. But I wanted to start to plant that seed for you today. All right, that is the lesson for today. Now let me go ahead and discontinue the PowerPoint. What you're going to do now is you've got, let's see, 35 minutes to be starting on 211 on my PLTW. And like I said earlier, I realized I haven't shared the OneNote in Teams. I was trying to do it while you guys were taking notes, but Teams keeps logging me out. So I think it's working now. So I should be able to share it with you. But basically what I'm looking for is you need to include your notes from today. So you can take a picture and put those into OneNote. And then you do need to do all the questions. So I think there's 10 maybe. Let me double check. 12. So there's 12 questions. You need to go through all 12 questions. If it asks you to fill in a truth table, you need to make the truth table. If it asks you to give an expression, you just need to show the expression. If it asks you other things, you're just going to do whatever it asks in those 12 questions. You do also need to do the conclusion, okay? And in the conclusion, there are 3 questions followed by a going further. And on the website, it says the going further is optional. But what I'm telling you right now is the going further is not optional this time. Okay, often it is, but this time it is not. Okay, I do want you to do the going further. And so this is in the midst of distributing this page to your guys' location, so you should see it soon. But when it opens up, it actually says in the instructions that the going further part is not optional. You do need to do the going further part this time. Okay? So in the next several minutes, it takes a little bit to distribute it, but in the next several minutes, you should see it popping up on your screen as long as that's working okay. Seems like it's working okay finally. And then I'll put a note on Axis as well so you can see the due date. It'll be due Tuesday night. If you have questions, you're welcome to stick around and work online and ask questions. If you think you've got it, you're welcome to be dismissed and just work on your own. It's up to you. Since we're already at 9:17, you don't necessarily need to check back in with me at the end. If you want to, you may. If you want to stay online, you may. But I think this is a fairly straightforward assignment. You're not really creating circuits or anything that you need to demonstrate to me. So if you do still need to show me circuits from the 126 and 127, you do need to be online to do that. But otherwise, you can be dismissed to stay online or not. And if you don't stay online, I'll see you next Tuesday and hope you have a great weekend.
See you.
Thank you.
You're welcome.
Thank you.
You're welcome.
So I may or may not have been multitasking while you were doing the notes. So I kind of made my own like 2-1